to solve some problems. So I was going to just work through a couple of problems from this part of chapter 6, and then after that, if anybody has any individual questions, I'll be happy to take those. Okay, so I'm using two different types of problems. The first is just a couple of problems that I pulled out of the standard chapter 6 PowerPoint that you already have that's on Moodle. The second is from Alex, and so even though it may not be exactly the same one that you got in your set of Alex problems, hopefully it's similar enough that you can answer those questions. Okay. All right, so one of the questions that I've gotten a lot from folks is about that Alex topic that's sort of reviewing and understanding the definitions of heat and work. And so I did want to go over that just a little bit. Remember, we talked about energy as being the symbol U. And so that's the total energy, or we say the internal energy, because that's all the energy that's in the system. Oh, let's see if I can spell. So the total, or the internal energy, is U. And of course, if we have a change in internal energy, delta U, that's going to come from two factors. It's going to come from any heat exchanged, right? So remember, heat is the exchange of thermal energy, and it's going to come from any work. Work is the exchange of mechanical energy. We can think about it that way. One of the pieces that we need to pay attention to are these, positive and negatives. I'm just going to reiterate this. If our system is expanding, right? So talking about gases, if our system is expanding, it has to do work in order to expand. Think about, if you are sitting down and you've got a 50-pound bag of flour in your lap, right? You have to do work to lift that bag of flour. You have to do work to stand up. However, if you're standing up and somebody throws a 50-pound bag of flour on you, you sit down, right? You collapse. And so that's work happening to the system. Expanding is work done by the system, right? And so work is negative because it's losing energy. Right? If it is contracting or compressing, and they say that's work done on the system. Rather than by the system. And work is positive. So those two things are here. When we talk about heat, we have some words that are particularly used to describe heat. And so endothermic is always going to be heat going into the system. Exothermic is always going to be heat going out of the system. And of course, if heat's leaving the system, if heat's going to the surroundings, then that's going to be a negative sign. If heat's going into the system, the surroundings are losing heat, losing energy, then that's going to be endothermic, and that's going to be a positive sign. So keeping those signs straight is going to be important. So here's a question that I pulled from Alex. Maybe you saw one similar to this. So it says that 109 kilojoules of heat flows out of the system during the reaction. So Q is our heat. It's 109 kilojoules. And if it's flowing out of the system, is it positive or negative?
Negative.
That's it. So Q, negative 109. And so they look at the piston as well. The piston does 225 kilojoules of work on the system. So W is 225 kilojoules. If it's done on the system, is work positive or negative?
Positive.
Positive, that's right. And so U equals Q plus W, negative 109 kilojoules, plus 225 kilojoules. And so U is 116 kilojoules. So let's answer some questions. Endothermic or exothermic, Q is negative, so it must be
Exothermic.
that's it. If the if it's exothermic, is the temperature of the water bath going up or down?
Up.
That's right, up. It's leaving the system. It's got to go somewhere. It goes to the water. Temperature of the water goes up. If the piston is doing work on the system, is that piston moving out or piston moving in?
It's moving in, right?
It's moving in, absolutely, Griffin. And then overall, does the reaction absorb or release energy? So this is U, right? This is W, and these are both Q. Is our U positive or negative? Positive. So is that absorb or release?
Is it absorbed?
Absorb.
Absorb for sure, right? And so how much do we absorb? 116 kilojoules. So the way that this is worded, absorb or release, you do not need a negative sign, even if there's a negative sign on the number, right? It's just asking for the magnitude, not the direction. So 116 kilojoules. And by now in this semester, you probably figured out Alex is pretty picky about decimal places. And so since this is a measured quantity, even though there's no change in the number of sig figs, Alex wants a decimal point after that number. Okay, so because Alex has a bunch of random questions, you might have seen one where you're given the total energy and something about the piston, and so you had to calculate heat instead of energy. You might have seen one where it gave you total energy and something about the temperature of the water, and so you had to figure out work instead of heat or total energy. But as long as we remember that U equals Q plus W, delta U equals U plus Q plus W, and we know that those terms, we're able to read those words and understand what they mean in terms of sign, we should be okay.
Can you go over how the piston moves again?
Sure. So here's our piston, right? If we are moving in on this gas, that piston has to push on that gas in order to compress that gas down, right? Remember, gas will fill whatever container it's in. That's one of the definitions of that phase. And so if we compress that gas down, it takes energy to do that, right? Think about if you've got a balloon and you try to mash it into a smaller volume, it doesn't want to go, right? It's hard to do. And so we have to add energy in order to compress that system. The balloon is the system and you are the surrounding in that example. And so whenever the piston is compressing those gases, that piston is moving down, it adds energy to the system because it removed energy from the surrounding, right? You had to use energy to compress that system, and that energy has to go somewhere. Remember that delta U for the universe has to be 0. Vice versa, if we heat up a gas, for example, and it expands, it's going to push against that piston. It's going to push that piston up. And so if the piston moves up, we know that the system has done work. And so piston out or piston up, system does work, right? That's our expanding part. And so W is less than 0. The system loses energy due to doing some work, right? And of course, piston down is the exact opposite.
Thank
Is that
you.
enough or you need more, Emily?
No, I got it. Thank you.
Okay. Anything else about this heat and work business? Okay. So this is the example that I left us off with on Monday. And I sort of jotted down this equation for you. Since we were talking about specific heat and heat capacity, the heat given off is equal to the mass of whatever we're talking about times the specific heat times the change in temperature. We sort of come up with this equation. We didn't know it to begin with, but I told you that the units on specific heat were joules per gram degree C. And so if we need joules for heat, then we know that our mass must be in grams and our temperature change must be in degrees C. Now tell me something about a degree C in a Kelvin. Are they the same size? Is one bigger than the other?
The degree, like the distance between degrees in both Kelvin and Celsius is the same.
That's it, absolutely. So, the difference from 14 to 15 Celsius is the same as the difference from 291, 292 Kelvin, right? Those are exactly the same size change, even though they're different numbers, right? And so whenever we talk about a delta T, it does not matter if it's Kelvin or Celsius, right? What I do not want you to do is to calculate this delta T in Celsius and then convert it to Kelvin, add 273 to it. That's a common student mistake. They think all temperatures have to be in Kelvin. But once we take a delta, it doesn't matter if it's Kelvin or Celsius, that delta is the same in either temperature scale. So I'm going to put here Kelvin or degrees C. So it tells us the mass of the water. It tells us the two temperatures. We can calculate temperature change. And we know from the other slides that the specific heat of water is 4.184 joules per gram degree C. That's a number that you'll probably memorize as you do some of these problems. And so if we were to calculate the amount of heat absorbed, it asks for it in kilojoules. So 466 grams of water times 4.184 joules per gram degree C times, we need to calculate delta T, and you could go ahead and calculate it and stick it in. I'm just going to write these numbers here, 74.6 minus 8.5. Okay. Then we can calculate Q. Who's got a calculator? Who's got a calculator? I'll do it, you do it. 466. And it's a big number in joules. We're going to convert it to kilojoules. How many sig figs should we have?
3.
3 sig figs, and what's our answer?
Is it 128,000 joules and then convert to 129 kilojoules? Oh, yeah. I'm sorry.
So
129,000.
Yeah. 129,000 joules or 129 kilojoules. Absolutely.
And you got the specific heat of 4.18 just from, like, where did that?
That's from a table that'll be given to you. The specific heat of water is one that we use an awful lot. And so, by the time you're done with Alex, perhaps you memorized it, but on the quest, you will be given the specific heat for water. Absolutely.
Okay, thank you.
Yep. Okay. So here's what that kind of question looks like in Alex. We have a water bath with 6.1 kilograms of water. Starts out at 28.1 degrees C. During that reaction, 132 kilojoules of heat flows out of the bath and into the flask. We're looking for the new temperature. So it gives us the specific heat capacity here. And so let's see, 132 kilojoules. Now, because this is in kilojoules and this is in joules, we need to do a little conversion. 132 kilojoules is how many joules?
One hundred thirty-two thousand.
That's right, 132,000 multiplied by 1,000. So 132,000 joules. Now, it's flowing out of the bath and into the flask. So is that for the, we're talking about the water here. So is that positive or negative?
Positive?
In
So-
respect to the water, negative.
Yeah, exactly. Respect to the water bath, it's negative. And so this heat is flowing out of the bath and into the flask. So what we're looking at here is the surroundings rather than the system, right? Our thermometer is stuck in the water bath, which is the surroundings. It's not stuck in the flask, which is the system, okay? And so because it flows out of the bath, this should be a negative value, right? So energy leaving the water bath. That makes Q negative. So how much water did we have? 6.1 kilograms. Again, our unit should be in grams. So that's 6,100 grams times 4.18 joules per gram to Kelvin, they say. The final temperature is what we're solving for, TF. The initial temperature is 28.1 degrees C. Again, the fact that this is degrees C in my temperature and this is Kelvin in my specific heat capacity doesn't matter, right? In this case, it doesn't matter. If you wanted to convert it to Kelvin, absolutely do it. But leaving it in degrees C is a-okay. I knew that it was the first value here that I'm solving for. Let me do that in a different color. I knew it was this value that I'm solving for because delta T is equal to TF minus TI. Anytime you take a change, it's always going to be final minus initial. So for temperature, final temperature minus initial temperature. When we talk about enthalpy of reaction, we're talking about the final enthalpy, which is the product, minus the initial enthalpy, which is the reactants. Okay. So now we just have to go through and solve. I'm going to do sort of an intermediate step. So I get 5.177 degrees C equals TF minus 28.1 degrees C. That's my intermediate step. And so if the question had asked you for delta T, you could stop there, right? Because this is the temperature change. Oops, I dropped my negative sign, forgive me. Negative 5.177 is my temperature change. And so I'm going to add 28.1 to both sides. My final temperature is 22.9 degrees C. And so, you know, it's always good to stop and think about an answer. It tells us that the energy left the bath, right, flows out of the bath into the flask. And so since we're talking about the temperature of the bath and the energy of the bath, if energy leaves the bath, then the temperature of that water should go down. Right? And it did. It went down by 5.2 degrees. So that's the same equation, solving for a different variable. Any questions there? Okay, The last thing that I think Alex has a question on for you is calorimetry. And calorimetry is when heat is transferred from one thing to another, from the system to surroundings or vice versa. And so since we know that the overall heat of the universe can't change, right? There's no overall change in the heat. There's no overall change in the energy of the universe. And so this Q universe has to equal 0, the change in the energy of the universe. And so since the Q universe is equal to the heat of the system, plus, remember, everything else in the universe is the surroundings. Right? And that has to equal 0. Because that has to equal 0, we can rewrite this as Q system equals negative Q surroundings. And so we already have that equation for Q. We can write M of the system, S of the system, delta T of the system equals negative M of the surroundings, S of the surroundings, delta T of the surroundings. Now, the mass of the whole universe, except for our system, is kind of hard to calculate. But that's when we sort of take into account that, you know, if we're doing a small reaction, and as long as it doesn't get too crazy, the heat from that reaction shouldn't really affect more than what's immediately next to it, right? It shouldn't affect the tabletop. It shouldn't affect the carpet in the hallway. It shouldn't affect the water fountain downstairs. All these other things that are part of the universe and therefore part of the surroundings that aren't part of our system. And so we limit it to, in most cases, the whatever water that it's in. So let's do one problem real quick, and then I'll stop this little problem session, and we can ask some questions. So we have some mass of naphthalene burned in a calorimeter, right? So calorimetry, measuring heat, right? And so we have this calorimeter, and we have a temperature chain. It tells us the heat capacity, not the specific heat, but the heat capacity of the calorimeter that includes everything, including any water, as 10.17 kilojoules per degree C. So we're calculating the heat of combustion of naphthalene per mole. Whew, what is happening? Right? So we're burning a small sample of this molecule. And all that energy is being absorbed by the calorimeter that molecule is in, that reaction is happening in. And so for a reaction, we don't talk about Q, we talk about delta H. Okay? And so heat of combustion, we think about that as delta H of combustion for naphthalene. It has units of kilojoules per mole, but Q just has units of kilojoules. So I need to multiply this by the number of moles of naphthalene that I have. That's going to be equal to negative my surroundings, right? So the mass of, in this case, water. Oh, I don't need to do that because I have the calorimetry constant. So the heat capacity of the calorimeter times delta T for the calorimeter. Okay. Where did all this come from? We left with Q system equals negative Q surroundings. How do we get to this? Remember, in Monday's class, we talked about how delta H is equal to Q. Right? And this is true. The heat given off is the enthalpy as long as we're at constant pressure. We add in this number of moles just so that the units work out. And so we can substitute Q of our system with delta H of our system as long as we know the number of moles. The surroundings, remember, is M times S times delta T. Again, we talked Monday about how if you know the mass and the specific heat, you can calculate the heat capacity. And that's usually a big C. And so this delta H is what we're solving for. We know that it's 1.435 grams and that it's C10H8. So we know the molar mass. So we can find the number of moles. So this is 1.435 grams times 1 mole is 128.19 grams, gives us 0.0112 moles. So delta H times 0.112 moles equals negative 10.17 kilojoules per degree C. And we have a temperature change of 25.95 minus 20.28. 5.67 degrees C. So we get negative 57.7 kilojoules is equal to delta H times 0.0112 moles. If we want to solve for delta H, we just divide by the moles. We get negative 5,150 kilojoules per mole. Okay. This one probably goes a step farther than the ones you'll see in ALEKS because it involves that delta H. But I wanted to do sort of a more difficult one now so that the easier ones on ALEKS you can handle, right? And so this is solving for the enthalpy of a reaction, in this case a combustion reaction. And we end up with an enthalpy of negative 5,150 kilojoules per mole. All right. Are there any questions about what this quest will cover? Again, it's going to cover the tail end of chapter 5. And so that's kinetic molecular theory, being able to look at those speed curves and interpret those. If I give you a blank speed curve, you should be able to label, which is the heaviest gas, which is the lightest gas, or which is the highest temperature, which is the lowest temperature. Using that equation for speed, URMS is equal to the square root of 3RT over M. And then the real gas part of chapter 5, where we talk about the difference between real and ideal gases, right? The part where they have volume and they actually have intermolecular forces, those attractive and repulsive forces between the particles. And then solving the van der Waals equation. The van der Waals equation is almost exclusively solved for pressure. The reason being because volume is a squared term in the denominator of that pressure correction. You end up with a cubic volume term if you try to solve it, and nobody wants to solve that equation by hand. And so the van der Waals equation is almost always solved for pressure. And then we start chapter 6. And so these sort of definition things of the first law of thermodynamics and internal energy and heat and work. And then moving into this heat transfer stuff where we calculate Q given heat capacity in a delta T, or we calculate delta T given Q and the heat capacity, like we've just done. I don't think we'll actually see any problems like this on the quest, this one that we've just done. But I think that you could run into it in Alex this week. And so I wanted to just have it in front of you in case you saw one that was similar. Okay.
Dr. Davis,
Yes,
I have a question about this problem specifically.
ask me.
So when I like read the problem and I see calculate the heat of combustion, like I understand now like why that's delta H. But when it says like on a molar basis, like I would think that like that mean we would need to like divide by moles. So how did you know to multiply by number of moles?
Yeah, so we could solve for just delta H for this particular reaction, right? And then we wouldn't have to multiply by the number of moles. And we'd get delta H is 57.7 kilojoules, but that's only for those situations when we have exactly 1.435 grams, right? And so that's not a very useful value for delta H for naphthalene. It'd be much more useful if we figured out delta H in terms of kilojoules per mole. And so when it says on a molar basis, what it tells me is that the units on delta H should be kilojoules per mole. And in order to get that, in order to get kilojoules, because we need kilojoules alone to match the other side, I've got to end up multiplying by the number of moles. So the units cancel.
Okay, that makes sense. Thank you.
Sure. Any other questions I can answer for you before we depart?
Well, I have another one if no one else has any.
Shoot.
Could you do an example similar to like there was like the ranking questions of like average speed of molecules, and it's given like their molar value, like how much we have, the pressure and degrees Celsius of like different gases.
Yep. Let me pull one of those questions up and I'll share my screen here. Or I'll shift my screen share. All right, let me do a switch. This kind of question?
Yes.
Yeah. So in our equation for speed, it's equal to the square root of 3 times r times t over the molar mass, right? Does the number of moles have anything to do with it?
Technically, yeah.
It's not in the equation for speed.
No, it's
Yeah, so the number of moles doesn't do anything. Is pressure in the equation for speed?
no.
No. So the only thing that matters is what it is, because that tells us how heavy it is, and the temperature, right? So this one that's at the lowest temperature. These others are all at -4 degrees. This one's at -35. So that one's either going to be the fastest or the slowest. Which is it?
Slowest.
The slowest one, absolutely. And so because I'm a teacher, I can't select this, but absolutely, that third row is going to be the slowest gas, right? So all the rest are the same temperature, so we can ignore temperature for now. between these three, helium, krypton, and xenon, do you know off the top of your head which of those is the biggest, heaviest?
Krypton, I think.
Xenon.
Xenon is the heaviest. And so is he going to be the fastest or the slowest out of those three?
Slowest.
The slowest. So xenon at -35 is the real slowest. Then xenon at -4. And then between helium and krypton, which is heavier?
Krypton.
Krypton. So he's going to be the next slowest, and then helium's going to be the fastest.
What if helium was -35 degrees Celsius?
Then you'd have to do the math. And they didn't ask. So all of these questions are arranged so that you can sort of rank these without actually doing the math.
Okay.
But yeah,
Thank
if helium went -35, you'd have to pull out a calculator and see if that is still faster than xenon at -4.
Right.
Okay. Any other kind of questions from Alex that you want to take a look at? Okay. Well, in that case, I'm glad you came to the problem-solving session today. I might try to do a few more of these where you sort of take a look at Alex's problems and maybe look at a couple more examples from the book as well on Wednesdays rather than just office hours. Office hours are fine, but they're not very well attended most weeks. So maybe this problem session will be more beneficial. All right. If any of you have individual questions, feel free to hang around, but if not, have a great Wednesday.
Thank you.
Thank you, Dr. Davis.
Thank you.
Take care.
Thank you.